In this video, we're going to look at higher order partial derivatives. So just linking back to what you should have learnt in single maths. Okay, your first derivatives, you'd write dy by dx, and then you'd differentiate that again with respect to x. So you could write it like this, to get d squared y by dx squared. Okay, like that. And that would be your second order derivative. Okay, we can also have second order derivatives for our partial derivatives, which is what we're going to look at here. So let's say we were considering the partial derivative with respect to x. We could write it using this notation here. Then let's say I went and partially differentiated with respect to x again. I would write f of xx like this. And then in terms of what I'm going to do, I'm going to partially differentiate with respect to x what I already had up here. Okay, so I would write it like this. And then that would simplify to the following, which is very similar to our ordinary derivatives, okay, to get this here. Okay, and that would be our first second order partial derivative that we've looked at. Now let's do similar for y, and you can probably guess, hopefully, what the notation is going to be. Okay, so there's our first derivative. Now, if we were to do our second one, it would be fyy. And then the idea is we are going to partially differentiate with respect to y again, of what we already had up here. So I'd write that in the brackets. And then simplifying it, I would then write the following. Okay, and that's the notation you're expected to use for your second order partial derivative with respect to y. Now, what we could also get is some mixed derivatives where we partially differentiate with respect to x and then y, or vice versa. So that's what we're going to consider now. Okay, so let's say we partially differentiated with respect to x first, and then we're going to do y. Well, I'd write that as f of yx. So our first derivative goes on the right. So just to be clear, that is the first derivative, okay, that we're going to do. So in terms of our other notation, I would write the following. The first derivative was the one with respect to x, so that was this one up here. So I'm going to write that here on the right. And then I'm going to take that and partially differentiate that with respect to y. So I'd write it like this. Then I could simplify that to the following. So partial derivative squared of z with respect to, and then I would write the following like this, keeping the x on the right because that was the one I did first. But let's do it the other way then. Let's say I partially differentiated with respect to y first and then did x. Okay, I'd write it like that with the y on the right. So I'd take the derivative for y and then partially differentiate with respect to x. So then that would come out as the following in the more simple notation. Now, those two derivatives are not necessarily going to be the same. Okay, they'll be different in a lot of scenarios. However, for the scenarios we look at in this course, they probably will come out as equal. And we have the mixed derivative theorem that states for most well-behaved continuous functions, those mixed derivatives are always going to be equal to each other. Okay, so what it means by well-behaved, well, that's a little bit vague because it's a bit complicated as to what that means. But if we're looking at continuous, if we think in the xy plane, what's a non-continuous function? Well, for example, our reciprocal one is, because I have to take my pen off the page in order to draw it. Okay, because at x equals 0, there's no defined value. Okay, whereas, for example, for a quadratic, well, that's going to be continuous. I can draw it without taking my pen off the page. Now, that's a fairly informal definition of continuous, but that's really all you need to know for this. However, do be careful not to muddle the notation, because when I've asked to calculate each of these, you need to make sure that your working is in the correct order. However, I do find that this theorem is useful to check your answer and ensure that you've got it correct. So let's actually just look at what these mixed derivatives are finding. Okay, so the one where it's y partial derivative first and then x measures the rate of change in the x direction as one is moving in the y direction. And then if you swap them around, well, the roles of the x and y there just swap around. So let's actually find some of these derivatives. Okay, so here's our question here. It's the same function from last time. So I've got the answers from last video just written here in order to speed things up. Okay, so part A, we need to find our second partial derivative with respect to x. Okay, so in order to do this, what I'm going to do is take my answer here from last time, and I need to partially differentiate this with respect to x again. So I could write the following. I could write that I'm going to partially differentiate with respect to x, and then write out the expression that I'm going to do. Okay, so remember x is our variable, y is held constant. So for the 2x, that's just going to become 2, because x is a variable, so it's a variable term. Then our other term also has x in it. Okay, so once again, it's a variable term. The power of x is what we focus on, it's 2. So I'm going to multiply by 2 to get negative 36. Then x will now be to the power of 1, and then the y will still be to the power of 3 like that. And that would be my final answer. Now let's do the second partial derivative with respect to y. So this time I'm going to use my second result from last video. So let's start with the 4y cubed. Okay, so it's got y in it, the power is 3. We multiply by 3 to get 12. And then it's going to be y squared. Then our second term also has y in it. Okay, so we go to the power of y, which is 2. We're going to multiply by that to get negative 36. X stays the same as the power, and then the y power reduces by 1 like that. Okay, so I've got my final answer there. So that's part B. Then part C is about our mixed derivatives. Okay, so let's do those next. We need to show that they're equal. So we'll do fxy. So this means the y derivative, the partial y derivative is first. So we got that answer here. And then we're going to partially differentiate that with respect to x. So if we got 4y cubed, and we're partially differentiating with respect to x, well, y is a constant. So this is a constant term, so this is going to become 0. Okay, so I will just write it in just for reference. And then for my next term, well, it's got x in it. Okay, it's a variable term. The power is 3, so I'm going to multiply by 3 to get negative 54. Then x is now going to be to the power of 2, 1 less, and then y stays the same as y squared. So the final answer is negative 54 x squared y squared, like that. Now let's do my other mixed derivative, so fyx. So that means you do the partial derivative with respect to x first, which is up here. And now we're going to partially differentiate with respect to y. So 2x, well, x is a constant, so that's a constant term, so that's going to become 0. And then my next term, well, that's a variable term. It's got y in it. The power of y is 3. So we're going to multiply by 3 to get negative 54. The x squared stays the same. The y cubed is now going to become y squared. Okay, and then if I ignore the 0, we get negative 54 x squared y squared. And as you can see, our two mixed derivatives have come out as equal. So I can say, therefore, fxy is equal to fyx as required.